Okay, we're going to start doing a mass moment of inertia via integration. So for this first problem, we're going to look at a torpedo tip. Why might we want to do this? Torpedo, as it goes through the water, would be rotating around the x-axis. That's beneficial for the navigation. So we have the torpedo tip, the radius at the base of this tip here is A, and the height going out to the front point, as it were, is H. Now we're given for this thing in the xy plane. I've revolved this in the picture, but if we just stayed in the xy plane, say along here, we have the shape is y squared equals a squared over hx. All right. Now you'll notice in this problem we're defined the radius of gyration, and I have x, emphasizing that we're rotating about the x-axis. So note, to get radius of gyration, we have to first compute the mass moment of inertia relative to the x, and then use the equation to back out the radius of gyration with respect to the x-axis. So we need to find, to do what's actually asked, we need to get Ix, and then we can back out Kx, the radius of gyration relative to the x-axis. Okay, so let's move on. So we're going to use the shell method, which we just talked about for the first time in our last video. And so let's see what that is. So here is our tip, and so the idea is we're going to use these shells that'll go from the base and extend out. So starting from 0 radius shell, it would go out at distance h, and as r gets bigger, this height of this shell will then just get progressively smaller and eventually down to 0. Okay? So if you look at this, what we're going to do is we're going to basically go along the y-axis, so we'll let y be radius, and so we're going to go from 0 to a. And so for a given y amount, the volume of a shell is 2 pi y, that's circumference, times thickness of the shell, that's dy, times the height of the shell, and that's the overall height of the torpedo tip minus this distance x. All right? But what is that distance x? Well, that distance x, for a given x to go up, we can find what y is. We have this equation right here. So we can solve x for y. I have that down here. There we go. It's right here. That's solving x for y. So when you do these problems, you just start saying, okay, what's the differential volume? And just bust down the parts. Pick the direction you want to integrate along, and so replace r with that variable, in this case y, 2 pi y. Thickness will be the dy, h minus x, and then you just put this in terms of y. Now when we go to do Ix, we can't just back out this radius of gyration. Recall there's an equation, Ix equals mass times k, in this case k sub x squared. So I need mass. So let's start this problem by doing mass first. And so here we have mass equals, basically this is going to be the integral of the volume, so integral dv, that'll give v, times density is mass. So here we have the volume, 0 to a, then here we have our shell. Each of the shells is a 2 pi y circumference. Here's the thickness, here's the height of the shell. Very simple integration in terms of y. And so we get rho h pi a squared over 2. Okay, so there's the mass. We're going to need that. Now for mass moment of inertia, let's think what that integral is going to be. It's the exact same integral with just adding in a y squared right here. That's the only difference. All right, well, I have that right here. Ix is rho, 0 to a, y squared, and then the same dv. Now when you multiply all that out, or integrate it out, you get rho h pi a to the 4th over 6. And that is equal to m kx, the radius of gyration relative to the x-axis squared. Well, we have the mass. That's right here. So we simply put the mass in, divide out. Here's what comes out of this thing. So here's Ix, here's mass, k squared. I'll add a little x here, little x here. Solve for kx, you get a over the root of 3. So If we had a pipe whose radius was a over the root of 3, you could replace that torpedo tip with an equivalent ideal pipe or shell whose radius is that. All right, so now we're going to do this one more time because we said there's two ways of doing this, and so let's consider that. So we're going to use a differential inertia and add them up. So Ix, we're going to compose Ix of differential inertias. Well, looking at this system, what would be a good differential inertia? Rather than breaking this thing up into shells and then going along the y-axis, let's just view a bunch of disks. We know what disks are. They are one, relative to this x, their mass moment of inertia will be 1/2 mr squared. All right, so this has 1/2 mr squared, but the m will be a dm. Because this is very, very thin, it'll be differential mass with very real radius. Okay, so that's what I have here. Dix is 1/2 mr squared. All right, so we have the 1/2. The radius, well, that'll just be the y. Okay, now what was the mass? Well, let's think about that. It'll be density times the area of this disk. Well, that's just a circle, so pi y squared, times dx, the thickness. That'll be the volume. Here's volume times density. All right, now this is going to move along the x. We're going from here to here, so we've got a little problem. All right, so these y's we got to put in terms of x. Well, that's really easily done because we had, remember, so here we have, I'm going to integrate this where x goes from 0 to h. Okay, remember that was the whole length of that was h there. So I'm going to go 0 to h with my dix. I have 0 to h, 1/2 rho. I multiply this out, pi y to the 4th. I need to put y in terms of x. But this was the original equation along the xy plane. Y squared equals a squared over h times x. So I'm going to stick this in there. That'll be a to the 4th and h squared, x squared. And we can see this right here. Okay, so I'll factor out the rho pi over 2, and I can factor out the a4th over h squared as well for that matter. But we just do the very simple integration in x, multiply everything out, and bam, here's our Ix. Same thing we had last time. And we'll note here just very quickly, we could have done an integral dm based on these little thin disks as well. And that's what I have right here. Rho times differential volume. So pi r squared was the area thickness that gave volume times r is mass. Bam, replace the y squared with the term in x, and we get the same mass. So this is an equivalent way of going about and doing these problems, and sometimes the integration is simply much easier, so it's a better path. Certainly disks are very easy to use and add up.